I somewhat foolishly agreed to give a talk on the history of 3D computer vision for a workshop in Italy a week ago, not realizing how much time this would take. Basically, I'm very familiar with a lot of computer vision and 3D computer vision in particular, but really trying to give the history of this problem, goes back decades. And so I had to consult a bunch of people to really get this right. So I immediately sent email to a number of the pioneers. Many of you recognize on this list, like Sri Nayar and Bertolt Horn and Andrew Zisserman and so forth. Basically, all the people you think of about doing pioneering work in computer vision, to try to get their input on what are the breakthroughs in computer vision over the years in the 3D domain. You want to close the door? Yeah. And so, of course, everyone sent me a different list. And all the structure motion guys sent me structure motion references. And all the photometric guys like Horn and Woodham sent me shape from shading references. And so everyone had a different interpretation of what is a landmark or a breakthrough. So I had to kind of cull from this some subset of things. And I think every one of these people would be horrified by the talk I'm about to give because it only covers a small subset of the references that they gave me for what they think are the pioneering references. So if you want to cover all of 3D vision, it's actually a very broad area. And so I had to select only a small number of things from each subfield. And so because I'm not going to cover all of this stuff, many of these emails I got from these folks were just terrific. They, really detailed histories over the last several decades. So I'm also going to post online their responses. So what does Bertolt Horn think were the canonical references in 3D vision and so forth? Okay, so in addition to these individuals who gave me some information, there's lots of good information online and in papers and so forth. And here are a few links if you're interested to know more about the history of photogrammetry or bundle adjustment and so forth. There's some good materials online. All right, so disclaimer, I've already said this a little bit, but this list is very incomplete for sure. It's also somewhat biased because it's my own interpretation of the highlights in 3D computer vision over the years, although it's informed by a lot, by experts, by readings, and just my experience over the years. I tended to select for high impact results like the things which I think have the biggest impact either in practice or on the research community. And so there's fewer kind of theoretical results, although there's a few in this list. And of course I'm omitting a lot of really important results just to fit this into an hour. Okay, so with that, let me jump into it. So first of all, a bit of so-called prehistory. So here are a few really important people over the years, the centuries up to now. So Leonardo da Vinci is not really he's by no means the first one to know about perspective, but he articulated it especially well. So I love this quote. Perspective is nothing else than the seeing of an object behind a sheet of glass, smooth and quite transparent, on the surface of which all things may be marked that are behind this glass. So he had the concept of a flat image plane. All things transmit their images to the eye by pyramidal lines, so rays, and these pyramidal lines are cut by said glass. The nearer to the eye these are intersected, the smaller the image of their cause will appear. So, really beautiful description of perspective, and had all the key ideas at that time. Okay, so another really important figure in 3D is Lambert, and you'll probably know him best through Lambert's law, which is really a model how light gets reflected off of it after it hits a surface, and it gets scattered in all directions for matte surfaces. And really, this has been the bane of computer vision algorithms because almost everything assumes Lambertian reflectance and therefore breaks down for anything that's shiny or specular or non-Lambertian. So we really have Lambert to blame for all these troubles in the field. But also, it turns out he was the first person who proposed inverse projection. So basically, figuring out where the camera was from one or more images, and that's also known as camera resectioning in the photogrammetry literature. Next on this list is Gauss, and Gauss is hugely important for all sorts of things. But one big element among those is least squares, and of course least squares is really fundamental to almost all of our algorithms these days, both linear algorithms as well as iterative nonlinear algorithms. And so it's been central to photogrammetry as well. Now, Wheatstone is maybe a bit more controversial to sort of put in the same line as these other three, but he was the first to really articulate the principles of stereo. And basically the idea that stereo consists of horizontal parallax between two images, between retinal projections. And it's kind of surprising that this wasn't known until the 1800s, and maybe it was. I mean, there's some evidence that Leonardo knew about stereo, although he didn't explain it as parallax. But what's interesting about Wheatstone's work is he was able to basically prove it by creating images, synthetic images, and putting them in a stereoscope. He invented the stereoscope, which then you could look at and see fuse a 3D image. So basically, that's a proof of this parallax concept. And of course, stereo has been central to a lot of major advances in 3D vision. Okay, so in parallel with computer vision, and actually predating a lot of computer vision, is photogrammetry. So photogrammetry is basically the science of measurement from optics, from some optical observation. I'm sort of sidestepping the word image because photogrammetry in some sense predated photography. So the mathematical foundations go back to the early 1800s. So Poncelet's invention of projective geometry, terms, things like the horopter, multi-view relations, and so forth. And I'll cover some of these later in this talk in the context of other computer vision breakthroughs. But the mathematics goes back a long ways. Practical use, people are interested in photogrammetry as part of map making and geodesy. And basically the idea is that if you're an imperialist country, you want to make sure that you can map the boundaries of nations that you're conquering and so forth. So people have long been interested in map making. And one of the great, maybe the biggest breakthrough in photogrammetry is this study called the Great Arc of India that the British, so when the British were surveying India, this turned out to be a huge undertaking. So the idea was basically to create a 3D map of India. So they took these huge theodolites that weighed a ton, literally a ton, through the jungles of India to try to take different measurements from different places. And they're able to show that that Mount Everest was actually the highest mountain on Earth. So it was thought before then that the mountain in the Andes was higher. But so this was one of the things that photogrammetry has to claim as a big advance. Anyway, so the way this was done was taking measurements from these different theodolites, triangulations, and kind of putting all these triangulations into a big manual bundle adjustment. So they had all these measurements between pairs of sensors, if you will, and they had to kind of bundle them all together by writing out the equations and solving for the relative positions of objects on paper. But this was an example bundle adjustment in the 1800s. Of course, this was advanced with the invention of photography around the same time, and they started putting these things together in the late 1800s. Okay, so now the next big events, I'm skipping a lot of big events here actually in photogrammetry, but when computers came about, computers that were big enough to do large least squares computations, photogrammetrists immediately saw the potential to use this for photogrammetry applications. So in particular, someone named Dwayne Brown pioneered the use of computers for bundle adjustment and basically triangulation efforts in the 1950s. And so you can really date back computer-based bundle adjustment to the 1950s, although at the time they weren't doing any image analysis. They were just using the computers to solve the equations, not to extract features or doing any measurements on the images themselves. Okay, so I call that all prehistory because there was no computer vision. There's no analysis of the images using computers. So let me talk about what were the first uses of computer vision for 3D measurement. And so, as far as I can tell, the first example of 3D computer vision is stereo. And this is work by this crazy inventor named Gilbert Hobrow. Basically, he was, at the time, the way photogrammetry worked, map making worked, is you had operators who would look at a pair of images and find corresponding points by hand, and then specify the displacements, and then feed those into a computer to solve for the positions of these points. And so Hobrow observed, well, wouldn't it be great if you could automate this manual correspondence task, because that was really the bottleneck. And so he invented this machine to do so. And so this is really an analog stereo machine, analog hardware, and it's pretty incredible. So I wasn't able to find original paper on this, but the patents are online. So here's an image from the patent. So what you're seeing here is basically a table with two images, slides on them, transparent images, and there is a CRT down below, which is scanning basically a spot across both images in parallel. And so it's illuminating a particular pixel, so to speak, in each image. And the intensity of that pixel is being picked up by a sensor, which is measuring the intensity in both images of the spot. And then there's a correlator, which compares those intensities and decides whether it's the same or not. If they're the same, then it knows the disparity based on the relative positions of the spot and says there's a match, and it gives you the disparity in the depth. If they're not, based on the difference in disparity, it will shift the beam in one of the images. Okay? So, and it would do this over and over again. So analog implementation of stereo, it's automated, and he had a series of innovations on top of this, and basically invented Lucas Canati stereo on a pyramid, back in the 50s. And for those of you who know a lot about computer vision, you'll know what I'm talking about. But yeah, this was rediscovered in computer vision basically, 3 decades later. But pretty amazing stuff. All right. So I'd say that was not very well known. Almost no one I've talked to in computer vision has ever heard of the previous slide. This one is very well known. So Larry Roberts, his PhD thesis in 1963 at MIT, he invented what's known as blocks world, so this phase of computer vision, where you basically take an image of a couple blocks, and then based on extracting where the edges are, which he did using a gradient operator on a computer, which was the first implementations of doing a gradient on computers. He's able to extract edges and lines, and then based on the relative orientations of these lines, he's able to figure out their configuration in 3D using a line labeling technique, and came up with a way to render the thing from a new viewpoint, as you're seeing in the far right, using presumably some kind of vector graphics. Anyway, so this is actually an incredible achievement in 1963 to do all of this stuff, to implement the whole thing and have it work, even if it only works for 2 blocks. But so Larry Roberts is often considered the father of computer vision. This title is often thrown around. So I went to his Wikipedia page to sort of see what it said about him. And actually his Wikipedia page doesn't even mention computer vision. So it turns out after his thesis, he stopped doing computer vision altogether. Maybe he was disgusted by it. And instead, he started working on networks, and he was he was the founder of the ARPANET, and is considered one of the 4 fathers of the internet. So that's what his Wikipedia page talked about instead of computer vision. But anyway, so this was a pretty impressive breakthrough, and one of the first results in 3D computer vision for sure. So, by the way, if people have questions, feel free to interrupt. There may be some people in the audience who are aware of things I'm missing, and any feedback is great. Okay, so this really fueled, Larry Roberts' work really fueled essentially a generation, or at least a decade of work on blocks world modeling. And the culmination of this, or one of the best known examples, was in the late 60s, early 70s, there's this demo, this system at MIT, where they tried to produce a robot which would basically take pictures in real time of blocks, and then based on that, construct a plan for building a structure that it just took a picture of from another set of blocks. So basically, you have a set of blocks stacked in a particular way. The robot tries to reproduce that exact stacking configuration from another set of blocks by figuring out the structure of the blocks as well as making a plan to navigate the robot. And this is incredibly ambitious because it basically involves solving the computer vision problem, solving the planning problem, solving the AI problem in some sense, at least the manipulation problem. And it turned out that most of this was doable. The weakest link was actually low-level edge finding in images. So kind of a disappointing weak link. And this really inspired people to work on edge detection, which they did for many years after that. So this really inspired kind of a dive into low-level computer vision, and all the kind of canny and similar results came out of this. All right, so fast forward. Actually, this is around the same time, actually. So Bertolt Horn, vision pioneer, so he did his thesis at MIT, and in 1970, he published his thesis, and this was on shape from shading. And this was one of the first methods that showed how from a single image you can infer the shape of an object. And basically the idea, as you can somewhat see in this slide, if you're depending on the projector, which is not so good on our end, but there are these curves superimposed on the image, and these are so-called characteristic curves or characteristic strips, where if you know the depth of the scene along one point on the strip, you can figure out the depth along any other point on the strip. So you can't figure out the absolute depth of the strip, but if you know one point, then you can integrate out the depth along every other point. And he also showed that if you have a network of these strips and you have certain boundary conditions, then you can actually integrate out the surface of the scene. So you can really recover the shape, in other words, the surface orientation and the mesh of the face from a single image, making lots of assumptions about constant reflectance and so forth. So this was really a key result. It turns out the astrophysicists were also doing similar things around the same time, around slightly earlier, around mid-1960s. There's a field known as photogrammetry, and their interest was they wanted to determine the shape of planets from an image of that planet. And so there's similar work. It's typically for profiles, so 1D instead of for full images. And Horn is really credited with one of the first to do kind of really 2D shape from shading. Now, for each of these landmarks I'm talking about, you can sort of trace some of the origins back many years before. So Ernst Mach actually formulated some of the basic equations behind this image irradiance equation almost 100 years before. But he actually concluded that inverting this equation, recovering the shape, was impossible. So it's kind of cool, at least, that Horn was able to prove him wrong, although I guess it took 100 years to do it.
Well, but I mean, wasn't he just saying that the problem was ill-posed and Horn regularized on top of it?
Well, so in some sense, yes, but he also thought that it was too unstable to even to get. I actually haven't looked at the original quotes of Mach, so I'm not sure. But the implication was that Mach didn't think it was feasible because you wouldn't be able to get boundary conditions or whatever. I don't know. Okay. It's a good question. This may be too strong to include that, but he had a quote saying it's basically impossible. All right. So another really amazing result from the 70s. So this is Bruce Baumgart's PhD thesis. from 1974. And he was the first to do shape from silhouettes. So the idea is that you have some scene and you have a set of photos, and you're somehow able to extract the silhouette of the object, the boundary of the object, separate the foreground from the background. In this case, you see this is an image of a doll. They're pretty low quality. These are scanned from his thesis. And so from this doll, here's a silhouette of the doll. Here's a silhouette of the doll from a different viewpoint. You can see it's actually missing the head. And this points to the difficulty of actually getting good silhouettes. And in this image, it's also missing the head. And so the basic idea is that if you know the camera positions for all these different views, then you can basically back project the images. So this is another great slide from his thesis. And so the idea is that you know where the camera is, you know the image, basically it's image plane sitting in front of the camera. If you trace a ray from the center of the camera through every point on the silhouette, that gives you a conical volume which the scene must lie in 3D. And so from each view you get a different volume which constrains the scene. And if you intersect all those volumes, it gives you an approximation of the scene. And so this is an idea, this is a figure which impressively shows that kind of intersection where you see the silhouettes at the end in the back projected intersection. So here's the results that he got. They look a little bit crude, but they're actually pretty nice. So here's the back side of the doll. You can see the head is missing, again, because it was missing in the silhouette. And this shows one of the limitations of shape from silhouette methods. If you miss a part of the object in any view, it disappears in all of views. So this figure, so each row is a different view, and the two columns correspond to a stereo pair. So if you're able to fuse these images, one of these people can do stereoscopic fusion, you might be able to better see the 3D structure from the image on the far right. But it's kind of cool, actually, in his thesis that he came up with the idea of doing a stereo reproduction like this. So in order to do this, you just think of how much he would have had to do on a 1974 computer in order to do this. He had to do the edge detection, he had to do the boundary following, he had to do the back projection in 3D, and he had to fit these polyhedral models to the back projection. Just that last part could have been a PhD, I think, in the 1970s, and he had to invent all these edge data structures, some of which are still in use today, to do the geometrical modeling. So a very impressive piece of work. And actually, his thesis is online, so if you go to this link at the bottom, I've tried to include links as much as I could to information online if you're interested in digging up more, these blue links on the slides. And I'll post these slides as well. Okay, so here's another example, I think, which looks a little bit better. Images of a horse, and you can see the horse model, which looks a bit more like a horse. All right, so I'm not going to go into details on these just because I'm probably not going to have time, but there's a lot of follow-on work on shape from silhouettes, and if you're interested, here's more where you can read on what the vision community has done, which builds on this basic stuff. All right, so I talked about shape from shading, Horn's work, but to this date, actually, the community has not been able to successfully get good results out of shape from shading. Maybe as Mock predicted, it's very unstable, and it's hard to get accurate results. You have to make very strong assumptions to make it work. And really, the only reason for including Horn's work as a landmark is, in my mind, is that it led to photometric stereo, which is this slide. So the key idea is that if instead of taking just one image, if you take, say, 3 images of the same scene from the same viewpoint but under different illuminations, those 3 images give you enough hues that you can reliably extract shape. And this works really well. So this is Woodham's PhD thesis. Bob Woodham was a student of Berthold Horn's. And this has an interesting history as well. So Woodham described this photometric stereo approach in his thesis, but actually he wasn't the one who implemented it. The first implementation was by a master's student, William Silver, in 1980, also at MIT. And this, you can see by the result that, so this is a reconstruction of basically an egg. It's not actually a real egg, it's a wooden egg. if you compare this model to all the other models I've shown up to this point, the details are spectacular. And if on the right is a profile of the egg in black, and there's a dotted line which you probably can't see very well, but the dotted line is the ground truth, the correct answer, and they're basically identical. So incredibly accurate models. So one of the people in computer vision, most people I think know about photometric stereo and Bob Woodham's work in particular, but I think a misconception is that people think it only works for Lambertian scenes. And in fact, they showed the very first work in his thesis and in Silver's implementation showed that you can use this for any kind of scene, any kind of BRDF, as long as it's not translucent. It has to be an opaque surface, but it can be shiny or it can be made out of whatever you want, as long as you know the form of that reflectance function. Okay, so and in fact, in Silver's implementation, what he did was he measured the reflectance function of wood, basically by having a reference object whose shape was known and taking measurements under different illuminations. And use this to reconstruct other wooden shapes. Okay, so as long as you know the reflectance function, you can use this method. It doesn't require Lambertian. All right, so photometric stereo, it works so well, it's inspired a lot of subsequent work in the community. And here are some of the highlights. Basically each one of these landmarks has like a series of arguably landmarks after them. So people who work on photometric stereo would say, here are the landmarks of photometric stereo. So I tried to do that for a couple of these subfields, but I'm not going to go into details just because I don't have time. All right, so okay, so the next major landmark is something called the essential matrix, and this was basically one of the first algorithms for recovering a scene from two projections under perspective. And basically the observation was, this is work by Lunge Higgins in Nature. It's actually cool that there is a Nature paper on entitled A Computer Algorithm for ... So basically he came up with the observation that if you have points in correspondence between two images, they're related by a 3x3 matrix. And in particular, there's a 3x3 matrix where if you take a point represented in homogeneous coordinates xy1 from the first image, and you multiply it by this 3x3 matrix, you get the corresponding epipolar line in the other image. In other words, the line in which its correspondence must occur in the other image. And this mapping from points to lines can be represented by this rank 2 3x3 matrix. And you can also compute camera matrices from this matrix and so forth. And so he came up with a linear algorithm for recovering this matrix from multiple projections of points. Sorry, two images, multiple points. And this is a very, very influential paper and inspired like a whole area of computer vision now known as multi-view geometry, with books by Hartley and Zisserman on Faugerat, and sort of this explosion of interest in this area in the 1990s. Now, it turns out that the theory, all the math here, can be traced back to mathematicians, notably Chasel, from the 1860s. So back in the 1860s, they actually figured out that there is a 3x3 rank 2 matrix which maps points in one image to lines in the other image. Okay, so this was known. They didn't have an algorithm that recovered these points because the mathematicians started working on algorithms. But it's interesting to note that a lot of fundamentals were known a long time ago. All right, so and then there's been a lot of subsequent work since then, stuff like the fundamental matrix. The essential matrix wasn't grand enough. You had to have another matrix, which is even more grand. The fundamental matrix is basically the uncalibrated version of this. The trifocal tensor is the 3-view case, and so forth. All right, so next major breakthrough. And this is an interesting one. I think it's probably not too controversial for this audience, but it might be controversial for some of the others. Is this really computer vision? So this is an algorithm called Marching Cubes by Lawrence and Klein, published in SIGGRAPH 1987. And basically, this was an algorithm to go from a volume to a surface. Very simple algorithm on the surface, at some level, but actually involves a fair amount of sophistication to get right. So the way it works is you assume you have a volume which implicitly represents the surface. So typically these are sign distance functions. So positive might mean outside, negative inside, and the zeros are the surface. So if you start at a voxel in this volume which contains the surface, and that basically tells you how to march in order to stay on the surface. So you start at a C point on the surface and you start marching over the surface. And then every time you march to another voxel which is on the surface, you create a polygon. Okay? And you have to figure out which polygon to create based on where the sub-voxel ISO function would intersect that voxel. Okay, so you do this at sub-voxel precision to create different sorts of polygons. And there's basically a table which tells you for every possible configuration of previous voxel and next voxel, the type of polygon to create intersecting which sides of the voxel. And so you have to get this table right. In fact, they didn't get the table quite right in the original publication. So if you implement this, make sure you look at the updates to this table to get it right. But and there's some earlier work. There's 1970s paper and so forth where they try to do similar things. But I think this was a big landmark, and it's something which is still in widespread use today. So it's pretty uncommon in our field, as you all know, to find an algorithm which is still used, more than 20 years on, so 25 years later, and this is an example. So an important landmark. Okay, so when I started, so we're actually catching up to where I actually started working on computer vision in the 1990s, and so really one of the things which really inspired me was this work by Tomasin Kanadi on structure from motion. And the basic idea is you're given a set of points over an image sequence, and if you know the correspondence of all these points, you can just put the point coordinates in rows of a matrix. Let's call it W. So the first row of the matrix would be the point 1 position, the x coordinate of the first point in all the images. The second row might be the x coordinate of the second point in all the images, and then you'd have a series of y. The bottom half of the matrix would be the y coordinates. So it turns out that if you have this matrix W, you can express that matrix as a product of the motion of the camera and the shape of the scene. And so the entries of the motion matrix are literally the camera parameters under orthographic projection, and the entries of the shape matrix are the 3D positions of those points. Okay, so this is basically a one-line solution to this structure from motion problem, being able to recover 3D from a sequence of images. So extremely elegant, very, very cool, highly influential. It turns out to be optimal under the right assumptions, an affine projection model, which is a version of orthographic, and inspired all sorts of follow-on work. These are just a few extensions to multiple bodies, optical flow that knows about 3D structure, non-rigid shapes, and so forth. Now it turns out that this hasn't really been picked up in modern structure from motion bundle adjustment 3D reconstruction problems because it only works for affine projection. It turns out not to work so well with outliers, and there's all sorts of caveats. But it's very cool that you can do this, and I think it got a lot of people interested in computer vision. All right, so next landmark on my list, iterative closest points. This was an idea which was simultaneously invented by 3 different authors. So I think this is evidence that the idea was kind of in the air, that so many people came up with at the same time. But the basic idea is that suppose you have overlapping range scans of an object, and you want to piece them together into a 3D model. You first have to align the range scans, and ICP is a way of doing that. And the basic idea of how it works, you have this green range scan and this red range scan. Over here, I guess you can't see the green at all. It must be the green pixels are knocked out of the projector or something like that. But you have correspondence between So the key thing is that if you knew the correspondence of points on the green curve and the red curve, then you could find the alignment between them. There's sort of a linear way to recover the alignment of the two curves. But you don't know the correspondence. So the trick is, for every point on the green curve, you find and you have an estimate of its current rotation relative and translation relative to the red curve. You find the closest point to that on the red curve, and then you assume that that's the right correspondence. Then you solve for the alignment, and then you get a better aligned pair of curves. And then it's not perfect because the correspondence was wrong, but now it's closer, so you then resolve for the putative correspondences and then iterate this procedure over and over again. And this actually worked quite well. And again, this is one of those examples that 20 years later is in widespread use. All right, so another really important result, 1995, this work by Sri Nair's group on depth from defocus. So here you're seeing a real-time range scan system, one of the first of its kind. And what you're seeing is on the left, there's a cup pouring milk into another cup, and on the right is a depth map computed in real time. And again, this is 15 years old or more, and basically what it's doing is it's taking two images with different focus blur. So the two images have different focus. One is out of focus in a different way than the other one because they're using different aperture sizes. And there's a different, no, I think it's actually focus settings. And based on the relative blur, you can figure out the depth of the scene. Okay, so so Nair's group wasn't the very first to invent this idea of defocus, but but this was the first, I think, really compelling system that showed how it could be practical. And another innovation here was typically when you take images with different focus settings, and you could try this with your own camera, when you change the focus, the magnification of the image changes a little bit. And so they came up with a way to make this really work reliably. They had to come up with a way to avoid this. So that they used a notion called telecentric optics, which allowed you to have two different camera paths with two different focus settings, which produced images with the exact same magnification. And so Nair also contributed this idea to the computer vision community, and it made a big difference. So this implementation, it ran at 30 hertz, accurate to 0.3% error. Very impressive again from 1990s. All right, so 1996, there's this work by Paul Dubovik and collaborators at Berkeley. This is this famous video that Paul made. There he is running. And he's holding a model of the campanile. There's actually sound on this of like bells ringing, campanile bells ringing. So there's the model, and now you're seeing the rendering of his reconstruction and the Berkeley campus modeled in 3D. So you can think of this as kind of a predecessor to Google Earth and similar products that try to do really high accuracy 3D modeling. And I think it's inspired a lot of efforts in this area. So going back and forth from the real footage to the 3D model. So you get a little dizzy watching this, but still cool. So I think this video really showed, I think, people what was possible in terms of realistic, really highly realistic 3D modeling from photos. So definitely a breakthrough, landmark result in the field. So in the next images you'll show, yes, you can see the real and the synthetic one right next to one another. Actually the model in that case. So here are the input photos of the tower and the photos of the environment, the Berkeley campus. And here's the model that they recovered. And you can see that the model is actually not very complicated. For example, the buildings on the bottom are just these boxes. But when you texture map it, it looks really good. All right. So this paper is important for a number of reasons. So it really coined, introduced, it didn't coin the term image-based modeling. I think this came from Leonard McMillan's work, but it introduced the concept of image-based modeling in the graphics community. And there is, some people argue that this work didn't actually have a lot of novelty. It was just an impressive system, but actually there were some really key innovations. So for example, view-dependent texture mapping, this is really the first use of it, which is now used routinely in Street View, for example, and was really the foundation for the Utopia work here. The model-based stereo, the idea of recovering crude geometric models, but recovering height fields on top of them. These guys came up with that and published that for the first time. And of course, it inspired a lot of interesting products that have come out of it. All right, so same year, range scan merging, also known as VRIP. This is like Tomasi Kannadi-like elegant result. Really cool method for, so basically the idea is that you somehow managed to align your range scans that now you want to fuse into a 3D model. So how do you create the 3D model from the aligned range scans? You want to create one consistent watertight mesh from all these partial scans. And the key idea here of this work is that there's basically a one-line solution to it again. So if you represent not a surface, but if you represent this surface as the level set of a 3D volume, where the surface is 0, and it basically every point in the volume is a distance to that scan, and you represent every scan as this signed distance function in the volume, then if you simply add up all the signed distance functions, one from each scan, and take the level set of that, that gives you the optimal surface in a least squared sense. Okay, so very elegant result, and this basically was the method of choice. It still is the method of choice for a lot of people. More recently, competing methods like Poisson surface reconstruction have come out, and people are starting to switch to those. But for more than 10 years, this has been really the standard range scan merging method. Okay, so of course I had to include my own PhD work here. That's why I have to give this talk as opposed to someone else, so I can inject my own thesis work. So 1997, was not just me, but Faugerat as well came up with multi-view stereo. And these actually, arguably multi-view stereo dates back further. Photogrammetrists had some similar methods for doing multi-view stereo in a decade previously. But in computer vision, these were kind of the main methods which came out in the late 90s for reconstructing high-quality 3D models from a set of multiple photos, not just a pair of images. And some of the key ideas in this work, both the space carving work that I participated in with Kyros Koudalakis and the level set work of Kervin and Faugerat, is basically to reconstruct a 3D shape directly instead of matching images, doing it in 3D space. Also visibility modeling. It turns out that figuring out which point is visible in which image is difficult, but if you do it in scene space the right way, you can solve this problem. And these were the methods that basically first described how to solve the visibility problem in a principled way with provable convergence properties and so forth. Okay, so these are important results in 3D in computer vision. So of course you're all familiar with graph cuts, or at least vision folks. And really the first paper that introduced graph cuts to computer vision and stereo in particular was Boykov's paper, CVPR paper from 1998. And this basically, this is a really cool paper. The algorithms are cool, but more importantly, I think that some lessons learned out of these papers is really cool. So on the left, you see window-based matching. These are depth maps, which correspond to depth of points to the image. So basically on the left is more or less a state-of-the-art algorithm at the time from '98, although it's not quite fair. There's better algorithms that they could have used. But this is a sort of kind of a simple method. And on the right is is the graph cut result, which is much higher quality. And up until this point, people had thought that stereo was a really hard problem to get the right correspondence between a pair of images. And in order to really solve this, you had to get better and better ways of comparing images, describing the region of pixels around the point of interest that you're trying to recover a correspondence for. So by coming up with better ways of describing pixels using edges and primitives and other things like that, you can get better matches. Now, graph cuts work basically said, forget about all of that. Take the simplest possible way of comparing images, basically taking the difference of pixel in the left image to a pixel in the right image, brain dead, but use a really good optimization algorithm. You can beat all this other stuff, just knock it out of the water. Okay, so this work really showed the power of optimization and ushered in the so-called graph cuts era for computer vision applications, all sorts of different problems. But in particular, it has been a really big development for stereo. Now, it also had its roots in the 1980s. This work by Baker and Binford, who, so I think people of my generation or older will say was a really important paper in stereo, but these days almost, I think it's kind of a footnote more than anything else. But they they were basically the first to propose global optimization for stereo, but they did it a line at a time using dynamic programming. But for basically 25 years or whatever, 15 years, no one was able to figure out how to extend this 1D optimization to 2D because the dynamic programming solution didn't extend. Graph cuts was basically the extension to 2D. I should also mention there's some other work around the same time, notably Roy and Cox, who came up with different formulations of graph cuts to do stereo problems. All right, so 1998, Mark Polyfides and his colleagues published a paper at ICCV on doing 3D reconstruction from basically a video camera, from uncalibrated 3D information. So the idea is you kind of fly around in this case, or you walk around the scene with a video camera and you get out a 3D reconstruction. You don't have to know anything at all about the video camera, none of the parameters, no calibration, nothing. So this is very inspirational work. It was really the same way that Tomasi and Kanadi was influential. I think this was also very influential. It's also the culmination of many research advances. The paper itself was on actually a relatively narrow topic of self-calibration, finding intrinsic camera parameters from a sequence of images. It didn't at all talk about the stereo, the texture mapping, or anything. But this is one of the key pieces that enabled them to put this whole system together. And also the community, the vision community as a whole, have been working through the 90s on solving this self-calibration bundle adjustment problem. And this is really one of the culminations of that work that showed you can put it all together in a really compelling system. So this is a big milestone for the field. All right, so 1999, Blends and Vetter at SIGGRAPH published this amazing paper where they showed from a single photo, you can create a 3D reconstruction that looks like this. So basically a laser scan quality 3D model of the person from a single photo. So harkening back to the shape from shading results, there's no way that shape from shading is going to be able to do this. So this is pretty incredible. Now, what it's doing is not using just image information, it's also using a database of 3D models. So what they did was they scanned 200 faces, 200 people, and they had this basically 200 scan vector space. Then through linear combinations of these scans, they can produce any other person who looks like anything like any of these 200 people. So that was basically their model. So instead of having to reconstruct the whole face, all they have to do is find 200 coefficients that are the best combination of these input people to this output person. And in fact, they were able to compress it a little bit more using principal components, and I think they only recovered around 100 coefficients. Anyway, so there's similar work around the same time, active appearance models, but I think these results are really unrivaled. Even now, I don't think there's better results in 3D reconstruction from faces. Now, if you look closely, you'll notice that the details may not exactly line up. Maybe Tom Hanks's nose is not quite this long, and it sort of depends on your input space and how well the the new photo lies in the space of input photos. But it gives a very compelling argument for using so-called model-based approaches for 3D reconstruction, which use strong priors on the type of geometry you're trying to reconstruct. So 1999 was also a big year in other ways. There's this Digital Michelangelo project. Marc Lavoie's group at Stanford and many other collaborators. And basically they set up to scan a bunch of statues and other things in Italy. And the centerpiece was Michelangelo's The David. And this was a huge scanning effort, probably the biggest scanning effort ever undertaken in terms of amount of resources and time and planning. It basically took a team of a dozen, I think there are 20 people involved total, working, scanning all night long. So first of all, they had access to the statue only at night because it's displayed in a museum. I think it's at the Uffizi. And the museum was closed at night, so they were allowed to scan all night long and had to stop in the morning. And so that's basically what they did. They scanned all night long for a month to get this model, and with roughly 20 people involved. So huge amount of work, but the result is beautiful. They've captured the sculpture basically almost every single nook and cranny at a 1/4 millimeter precision. And so you can zoom in. On the right, you're seeing zooming into the eye of the statue, and you can zoom in further to this like ridge and see the details of the mesh. And so impressive results. There's also other scanning work like the Pieta project around the same time. But this is really shows what you can do with 3D laser scanning technology, and also how much work it is to use it. Okay, same year. So camera tracking. I was looking for the canonical reference on bundle adjustment. It was actually really hard to find a canonical reference on the computer-based bundle adjustment, and so I went with this. This is really the first time practical bundle adjustment systems were used in an application. So for all these, basically for almost every special effects scene these days, there's a combination of real footage and computer graphics. And doing that right involves figuring out where the camera is precisely in the shot, so you can overlay the computer graphics in the same place. So this process is called match move, and it requires bundle adjusting or reconstructing the positions in all the cameras and all the images. And so the first truly automated methods were developed in the late 90s for doing this, for actually tracking the images and doing the 3D analysis. And so there's some pioneering commercial systems, in particular Match Mover came out of INRIA, Faugerat's group, led by Luc Robert, and Boujou grew out of Oxford, Fitzgibbon and Zisserman and so forth. There's also concurrent work in photogrammetry around the same time. Let's see, so I'm running a little bit low. I'm just going to skip over some of these. There are some important benchmarks for stereo that came about in 2001. Some really elegant work for doing stereo with non-Lambertian surfaces in 2002. 2003 is the year I'd like to say stereo equals laser scan. So this is the first stereo computer vision, passive computer vision method, no laser scan, that could produce 3D geometry that looked as good as a laser scan and arguably is almost as good. And this was Carlos Hernandez's work, and Carlos, as you know, is at Google now. Very cool work, which inspired a lot of subsequent work, which I'm just going to skip over, including Yasu's work, and others in the community. 2006, first work on reconstructing 3D information from photos on the internet. So this is our phototourism work, which led to Microsoft's PhotoSynth. And really the key ingredients to make this work were SIFT, these reliable feature points, and the progress in photogrammetry over the years. And there's similar work by other authors. 2006, there's a really cool effort of creating 3D models of a city by just driving a car around. And so it's kind of like Street View LiDAR, but just using raw computer vision measurements instead of LiDAR. This 2008, there's a great paper by Zebedin et al., Bishop's group, and there they showed basically an automated version of Paul Debevic's facade. So from aerial imagery, it creates this really, really impressive 3D model of a city completely automatically. 2009, Samir did his Roman a Day work, and this is sort of city scale structure promotion from image collections. And sorry, I don't have more time to talk about these. And of course, 2011 is Connect. So body pose from a single depth image, 200 frames per second, fastest selling electronics device in history. So they had, in the first 3 months, I think they had double the sales of the iPad when it came out. So not bad for a computer vision system. Of course, it has other things aside from computer vision, but we like to take credit for it. All right, so in 2013, there was this fantastic work on basically digital Michelangelo from a few photos. So instead of having to scan all night long, this group was able to just take a few photos and create a model of digital Michelangelo that had the quality of this Lavoie group that took a month. In 2015, there is this wonderful project on creating a public repository of the world's geometry, where basically they scan everything, people's places and scenes, things, and put it all in a publicly hosted web site. 2015, this work on, which I'm sure you all remember, of how to reconstruct yourself from your photo collections. So it took all of your photos of your poses, expression, body shapes over time, and created a 3D model, perfect 3D model of you and all the ways that you move. 2020, it took a lot longer to solve this inverse CAD problem. So the idea is to create what an architect would call a 3D model from not just a point cloud, but an accurate a 3D model which captures the salient features of the scene: walls, floors, small number of polygons from raw point clouds, fills in the gaps, easy to edit and modify. 2020, we finally solved the visual Turing test. So this is creating a 3D computer vision system which creates models which are truly indistinguishable from reality, where you're able to move however you want through the scene and it still looks perfect. It still looks just like being there. And finally, in 2030, the computer beat the human. That's it. Thanks, you guys.
Thank you very much for bringing it together.